So this one is the second Okamase class that we will look into the confined concrete model. The reason why we're gonna look into this first because the next step we will get into octave, and then we will start the moment curvature analysis of the cross section. So last time we actually did just at one condition, which is at the failure defined by ACI, but now we are going to do the moment curvature response, okay, to create this, which is extremely useful for you, and we will incorporate the concrete model, which is well, the sophisticated one, okay. So the confined concrete, in the core you will use one model, and the unconfined concrete, which is outside the core, we will using the other model. All right, so we'll be able to track the response of the structure through, and that will be, yeah, you will enjoy that. That's gonna be very useful for you if you do concrete design. So this paper, actually you can look into Scott's dissertation that actually I showed you last time. But anyway, all right, we can look into this one also. So this one is from ACI Journal, Stress Strain Behavior of Concrete Confined by Overlapping Hoop at Low and High Strain Rate. Generally what we are going to use is just for the low strain rate. All right, and actually this paper is, well, based on first of all Park and Kent. All right, the concrete model that was used to compare with the results here was Park and Kent, and then modify Park and Kent. For Scott Park Priestley, they run the test at different strain rate. The thing is that, well, in conclusion, this paper ends up with the conclusion that the high strain rate is affecting the concrete constitutive relationships. So you expect higher stress, ultimate compressive stress of concrete at high strain rate. Anyhow, if you look in this Scott paper, I think they also show the Park. They show Park and Kent. That's what we looked at last time, and modified Park and Kent is also here, I think. So we can, right? Okay, so this was Park and Kent we look at last time. So look at all of this. The difference you expect from first of all the model here, it has the effects from the confinement. Okay, so the rho S is introduced. Rho S is the volumetric ratio between the confining hoop to the confined core. But the thing is that the model we see over here, it does not incorporate the benefit in the strength. So the confined core just produce the ductility from one unconfined to the confined one. You get the extra ductility, but you didn't get extra strength from this model. So later on the Park and Kent model was there was a proposal to upgrade this to the new one. The new one is bigger than this one, so over here it is the K times F prime C. So the Kf prime C, you see the coefficient K in front of F prime C. This one is greater than 1 for the K value, and the K value could be determined from the ratio and configuration of the hoop reinforcement. So that will incorporate, and okay, you come up with the K, right? And the value here will be a little bit different, which is modified by K. So basically the backbone looks pretty much like original one, Park and Kent, but you have the modification, which is the K modification. So let's take a look at this one. So where is it? Modify. No, not this one. Okay, modify Kent and Park. Okay. So now the maximum stress has increased from this point here for the Kent and Park. K is equals to 1, right? So to this one, so you get the increase which is coming from the K value. And you can also see that not only just the peak stress that is modified, it's also the peak strain. Because of the hoop, you get some extra ductility, so you can achieve to this point, okay, whereas this one was just back there. Okay, so not just 2000 microstrain, you get 2000 microstrain multiplied by the K value, right? And the other parameters will be calculated, and you get the effect of the K. This one got to correct the sign. If you refer back to the Park and Kent, you see that the sign is the negative sign. Okay, so if you come across this literature, if you download it, then this must be the point where you need to put some correction. And then this normalized ratio, you have the K embedded in there. Okay, so that shifts your curve a little bit. You have the K scaling in front of the F prime C. Likewise, for the declining slope, declining curve, after you reach to the peak, you have the K as well, F prime C, Zm. Okay, but you can see that the calculation here is sort of more complicated than the one before, due to the fact that well, more experiments was carried out, and they are more precise in this. So what you need to input, not only just concrete parameters, but rho S. Rho S, how to come up with this rho S? So let's take a look at this here together. So you have the rebar, longitudinal ones, and okay, so you have the green line that represents the hoop. Okay, so the confinement is given there. So if you want to get the rho S is the volume of it is the ratio between the volume of the steel hoop, and then that divides by volume of the core, confined core. Okay, so the confined core, okay, first of all, for the hoop, so you look at one hoop, right? You know the AS, and then you know the dimension in this and dimension in this direction. You have the B, you have the H. So basically it is AS multiplied by 2 and B plus H. This is the volume of the steel confinement. Whereas for the core being confined by this steel, we have the spacing between the hoop. So the spacing which is I think SH, yeah, I don't, let me check into this one. No, not this one. I highlight there are so many H is the width of concrete core, SH is center to center spacing of hoop. Yes, okay. So this is S, what? S subscript H, okay. Right, so the volume of concrete is to be calculated by B times H times SH. Right, this is the confined core. This is volume of the steel. So take this volume, this one, divide by this one. Turns out to be 2AS B plus H divided by BH SH. Okay, so you come up with rho S. Well, if you have some other sort of reinforcement in this layer, in maybe your hoop system is more complicated than this one. For example, if you have the column and then you have some confinement, okay, like this, because if you don't have well, this H, if it is too large, then the effectiveness of the confinement will be reduced. Since the rebar here, actually hoop, the most effective one has to be the circular shape, but when it is in the rectangular shape, when the pressure comes out, you are under the bending. So the small space, small area, small length like this, okay, will be more effective. That's why the longitudinal steel might be placed also at this point, and then you have something to help confine, so it will go like this, which is more difficult than going out this way, right? So well, this has less stiffness if you well, look into that view. Confining effect is relying on the stiffness of the hoop system. Okay, so you will need to incorporate this steel, okay, into your calculation if you have some other things aside from the rectangular shape hoop. Okay, so we just throw in everything into this ZM, and then you get the post peak behavior of your concrete. So now we are going to shift back to Octave, and we will construct everything. You just need, yes? Physical meaning of the K. The point is that it actually should be included. Actually, in Park and Kent they didn't include. It should be included because you have two things. You have two things in comparison. First of all, you have the cylinder specimen, okay, and then you put it. It's just a pure cylinder specimen without any confinement. I'll draw it. So cylinder number 1, and then you have cylinder number 2. Cylinder number 1, you have nothing, no steel confinement, whereas the cylinder number 2, if you coil the steel up and put it inside, what happens when you crush the specimen for cylinder number 1? You get this that we talked about last time, the hourglass shape, because as it is not confined, this part just fall and split. Because it forms the maximum tensile stress plane, so the concrete cannot bear that. It cracked and it fell like that. It does not fail actually by the compression. The failure plane is from the tensile stress, right? So if the problem is about the tensile stress that make the system non-ductile, of course we know that under tension concrete is very bad in ductility. So the spring over here, the hoop reinforcement over here will secure the surrounding concrete. Okay, and then the failure will turns out to be in this shape. You'll be seeing your hoop like this. Maybe around this area it will be pretty much in the shape like this. Okay, because the hoop produce if it is a zoom, the hoop produce the compression strut to confine. So when it breaks in this form because compression strut comes out in the angle like this. So this versus this, that is the physical meaning of the K. That's how K comes in. So if you break by this, then you get the F prime C. But if you have this, then this Mr. K, which is the part that maintains. So after this point, then you have the degradation of the concrete inside this confined core, and then it will be the ductile mode of failure because the steel hoop start acting together with your concrete. Before the curve reach to this peak, actually the participation of the confinement might not be so high. I mean, if you put the strain gauge in a steel hoop, okay, and check the strain of the steel versus the strain of concrete. Okay, concrete undergoes the strain in this direction. Steel is in the orthogonal direction. Steel wouldn't supposed to act or carry anything. So in the initial part of the curve of the concrete, okay, initial part here, participation from steel is not so high. But in comparison with the condition after the concrete reach to the peak and then it start formation of the cracking, micro cracking, crack propagation inside. Once that cracks occur, which means the tensile cracking, right? Because you have some plane subjected to tensile stress. So that plane cracks, it moves, and when it moves, you get the force in the steel confinement. So maybe we can look up, if you read carefully in maybe this literature or some other literature, we might be able to see the plot versus between the steel strain versus the concrete strain, like this, epsilon C and epsilon S. So the first part will not be much, and then once the crack forms, then this part will pick up. But the thing is that since the people feel like the mobilization of epsilon s is not much in the initial part, okay, in Park and Kent original one, they do not incorporate the effect of the steel before the ultimate capacity of concrete. So that's it, right? But I think this picture should explain you well about why you get the hero K. Okay, how does the K come in? All right? Okay, so I move to coding for the cross section. So the issue came up. Let's take a look at this. So the hoop, okay, which is a confinement, the question is if this is going to help resist, right, the rebar buckling. Like this, right? That is the question. Okay. The rebar, main rebar, longitudinal rebar. Buckling. Longitudinal rebar buckling, the concept actually is not that special. Actually, you can derive and you can come up with the number recommended in ACI about the spacing between the stirrup that will help carry the rebar and help, we call it prolong. Rebar buckling. You cannot prevent, you can just prolong. This you can see the spacing, right? Your rebar area is AS, nominal yield strength Fy. The thing is that you need your rebar to mobilize compressive strength up to Fy. So AS Fy has to be, well, you equate it, okay, or actually it should be guarantee. So less than what? P critical of this bar, buckling load. Okay, buckling load of rebar. How to compute the buckling load of rebar? This picture, it depends on the fixity. If it buckle this shape, right, it will be equal to S. But if you can see that this is a continuous system, so it might be like this. So this is equals to 2 times of the well, basically it is S over 2, right? So it ranges. This is the conservative case. We don't know, okay, what exactly is the condition, okay, but you have 2 extremes. First extreme, this one. Second extreme, you have 0 rotation here, and then you gain the maximum. Maybe it will be somewhere in between, of course. Then PCR is equals to, if you still have some knowledge in computer method, you get pi square E, which is ES and I over L square, so it is the S square. I, what is the I? For pi what? Circular cross section. What is it?
Pi over 4, 64 pi over
Well, we don't need to memorize things. Okay. Second area, moment of inertia, circular. Circle. Okay, pi r to the fourth over 4. Okay, which is a pi d to the fourth over 64. Okay. Then plug in. AS Fy has to be smaller than pi cube ES D. Oh, whoa. Okay, pi cube ES and what I. Okay, D to the fourth over 64S square. Am I missing something? No. Okay. We want to determine the S, right? Has to be less than square root of. So you have 1 pi and you have 1 pi out there. ES D square is out there, right? And then what? Fy AS. Okay. I think we will do this first. Okay, don't jump. We have pi cube ES D fourth 64S square multiplied by 1 over Fy is there, AS is the pi D square over 4. So the D fourth cancel out with D square, pi cube cancel out, you get pi square. 64 turns out to be 16, right? The whole thing is in the square root. So this is less than pi square, we can bring it out to pi. 16 will be 4 inside ES. D was taken out to just 1, right? You have S square is on, S square was on that side. S square, it shouldn't be here. What else? Fy, is that it? I think that's all. ES, same unit, can normalize, right? So ES is 200 GPa. Fy is 400 MPa. Okay, so we are in the same unit. Cancel. Up there is MPa already. So 5 turns out to be 500, right? Inside the square root is a square root of 500. Pi over 4 times the D. $500, you get 20, you get 400, right? 22, okay, 22 divided by 4, you get somewhere 5.5. 5.5 multiplied by pi, you get 0.5 d. S has to be less than this figure. Still large. I remember that it was somewhere around 4 to 8 diameters from this calculation. Is there anything? Or maybe Fy could be, yeah, larger Fy number is larger. Okay, I think the Fy I used to play with is half of this one, so smaller, but that will make it say 1.4 times less. If the Fy is reduced to that will be even larger. Let's see a bit more. Is there anything possibilities? Or 64 a square as Fy as, okay, came in pi d square over 4. Okay, Fy is there. Es d square d pi over 4, pi over 4. Yeah, it's not that far away. So S has to be less than this number, 17 times of the diameter. That means for the diameter of 12, it has to be less than 20 centimeters about. Yeah. ACI require this number to be less than how much? 30 d 30 centimeter. That is times the diameter in ACI. What was number of times of the diameter? Well, fine. You can look up for this figure precisely later. The thing is that it is computed by just checking the buckling of the rebar. Okay, so to prolong the buckling, we add the hoop. Hoop does serve as the confinement for the concrete core, and at the meantime, hoop also put the locking and limit the space or the length, effective buckling length of the rebar, such that the longitudinal bar will not buckle at very low stress. Okay, but the concept and the derivation will be coming into this way, but precisely what number I got to go back check some notes. It will not be far from this. Maybe some little assumption somewhere. Okay, so is Fy? No, fine. I don't know if they use higher Fy then. If the Fy is high, then the space will be short, right? So it will be conservative. Fy, nominal Fy is generally less than the actual Fy. So, right? So if the rationale for coming up with this length, okay, is to put the as high as possible Fy to control to that limit, then it will be shorter than this number. But we will come back to precisely to the question. So this part here help limit this effective length of the rebar, but it can just prolong, because when you apply compressive stress to your RC member, your confined core has the pressure and it tends to push this outside anyway. So at the very last condition of the concrete failure, you will for sure see the rebar buckling no matter what. No matter how much the reinforced hoop reinforcement you add in, but still when concrete bursts out, you have two phenomena. First, concrete itself produce the pressure, and the second, the hoop breakage is also expected, right? So concrete push the hoops out, the hoops under the tension up to the ultimate condition, hoop breaks, and you will see the rebar buckling clearly. So it prolonged because you don't want that to happen at early stage, but at this ultimate state it is unavoidable. It has to go this way. But at very low load and your rebar is very slender, the longitudinal bar is very slender, that is the condition that is totally unfavorable. This is what version of ACI? 16.1?
ACI section 7.1.
Or 7.1? 0.5? 0.2. So this is 16, right? 16 times the diameter.
Spacing not to be greater than 16 mm.
Okay, right. Yeah, I just remember from the class note when I was studying that I saw the number 4 and number 8 for some reason. I'll got to check that notes. Okay, what is 4 and 8 for?
So it is written that in building columns generally are proportion with ratio of length to cross section 8 to 12.
8 to 12. Okay, right. But
For high strength steel and slender column.
the higher
Highest.
the higher strength, the less parameter, so it will be reduced to 8 to 12. Okay,
Higher strength and more slender column.
more slender column. Okay. For a more slender column, okay, because the slender column you have more chance for elastic buckling of the overall column, and that will concentrate the moment, that will produce a second order moment in some area. Okay, so in that some area, well, you will not expect the uniform compressive stress for short column and slender column of which the size is like this, same size. Small column, you have small second order effect. Slender column, larger second order effect, so it tends to buck when the column has the component of the moment. When the component is large, then your cross section, some zone, okay, one side is under compression, high compression, and the other side is a tension. So this high compression is is very high compared to the P over A. So for the case like this, that could be the rationale. Well, to make it clear, to make it sure, read the commentary. But from the physical point of view, I think it is the rationale is based on that the column, slender column, will be subjected to this high compressive stress. Well, this could be applicable to the beam case where you have the high strain that the code mentioned. For example, the plastic hinge zone. So that you expect the high strain in this plastic hinge zone, right? Because plastic moment mobilized over here, large strain, large compressive strain is expected here. So you will also need to provide some sort of extra, the spacing will reduce due to that fact. Okay, so not far. Okay, we're in octave now, so we will come down into this working folder, okay, which is the same working folder as before. Let's just make a subfolder in here for the, well, what is frozen? Okay. What is this? C. Okay. I will just do a little copying from here. I'm gonna modify the code I have from the frame analysis before. Okay, it is here. All right. Basically, over here we need to construct the input and output. Why is section o1.txt? I don't think I need .txt. Okay, right, this is a text file. I will open it up from here. So it opens up here. We will give the geometry of the cross section. It will be fully automatic, unlike the one I made in Excel. Well, that has to, well, got to blame me. Right? I'm not doing the Visual Basic. If I do Visual Basic, it could be automatic there, but too much in my brain. I don't like the syntax in Visual Basic. Yeah, that's one thing. Something and then dot, something and then dot. That sort of structure is annoying to me. But well, that is because of me, not because of any other thing. Just my problem. So what do we need? I think for the first of all, let me just take a glance of the order. Well, this one. Okay. Problem cross section number 1. The 12th of, right. Yeah, this is good to do because at least you have some idea when this was created, when was this one done. So the first thing, we will need the information about the discretization. So the discretization along the vertical direction, that is the number of slices you have. Okay, so I will give the number of slices, number of discretization along the thickness. Okay, so the total thickness, total height of the member will be given here. I have like 100. It's fine, the program does the job. So it's gonna construct the cross section of which the number of discretization is equal to 100. The thing is that we will okay, you will see how things done. Next thing is the number of steel reinforcement layer. The thing is that I'm thinking about the algorithm and the architectures of the data. That's why I was quiet for a while. I was trying to see what will be the best way to and the easiest way to deal with this guy. Number of steel reinforcement, go ahead, 5, 6, flexible, right? Next, what else? Compressive strength. We can rearrange all the things. Compressive strength of concrete cylinder strength MPa. What? 35? What else? Yield strength. Yeah. Tensile yield strength of longitudinal reinforcement MPa 400. Elastic modulus of steel reinforcement. All means like longitudinal and transverse. Actually, it will be the same. MPa. Yeah, MPa. So it has to be 200. All right, 200,000. Well, we got to check into the fine. Stir up. We have, but I just going to put things in one by one. I mean, I'm thinking of the data structure just a bit. First of all, I think of the geometry, construction of the geometry of the cross section. So number of discretization along the thickness 100. Okay. Steel reinforcement, number of layer, but we can also put more in the geometry, like number of rebar longitudinal rebar description in each layer. So layer number 1, data structure, number of bar and diameter in millimeter of the bar, and then you have 6, right? You could have 4. The second one is 2, 2, 2, 2, 4. Okay. And the number, okay, we get the diameter of the rebar. You might have 25 millimeters, 20, 20, 20, 20, and 25. Make it a little more, make it 6. That will be very crowded. Anyway, we can make a big cross section. There. Right, still remember reinforcement. 100 is going to be sort of headed for you. The point is that should we just list it down here? Yeah, I think it should be like that. So we list it down here. I make it 20 or 30. We can generate these parameters, this description in Excel, and then copy and paste it here. Number of discretization, this one is going to be like the concrete slice description. Data structure thickness. Which is millimeters. And then width, top, width, bottom, all Okay. So this makes sense if we have thickness slice by slice, and then at the top and at the bottom you have the freedom to make it, for example, if it's gonna be in the shape. The thing is that yeah, it could be averaged out when we talk about the stress integration. Okay, I will average it out that way. Now I think we go ahead use the Excel to create this. Let's play with the T cross section. So the top of the T, we will discretize the top part using small mesh size, and the bottom part, that the how to say, the part below neutral axis approximately. Okay, this part here should be under tension, and it will contribute nothing to the force resistance. So less discretization at the bottom part. Okay, so let's do this. So first of all, thickness of the slice, the top of the T, let's make it 10 centimeters thick, and the vertical part of the T be like 50 centimeters. Okay, 50 centimeters in height, and the width is 10 centimeters. The flange width, T flange width is too much things in the air, so draw it out a little bit. Okay, so here this T, okay, the thickness of this part is 10 centimeters. The width make it 40 centimeters, and then the height here is 50 centimeters, and the width is 10 centimeters. So 10 centimeters, we cannot stuff that thing in, right? We can do this. Okay, make it T like this. So this top layer here, I think the discretization in 10 centimeters makes sense. Oh, we need millimeters in everything, right? 10 millimeters. The top width is 40. Bottom width is also 40. First part's done. The second part here, I think I'm gonna break it into 2 pieces, because I think the stress block will not come down below this point here. The top 20 centimeters will be finely discretized, whereas the thing below will be the coarse mesh. So over here I have 20 centimeters. I have 20 more blocks down to here, right? 10 again. This number is 100 millimeters. Okay, and then the next part, 30 centimeters here, that's gonna need I make the layer thickness to be 3 centimeters. Okay, and then this part here at the bottom, if it is 150 millimeters in the thickness of this bottom flange, so you have 5 layers, but the width of this thing is 30 centimeter. The top is 40. Make it a little bit bigger than 500. Okay, right, in total how many layers? I have 45. Copy this and we'll paste it there in the editor. So I have 45 layers. Then number of steel reinforcements 6. This one will be distributed. Diameter and this from top So from the top, this is just 10 centimeters, this one, so 5 is 50. Okay, change to 12 then. We're gonna have some other things more, like the sort of covering. Right, we can add everything in, and then we can just use the free, not free, okay, it takes a lot of knowledge, but you don't need to buy the software for the RC, cross-section analysis. So 12, and that is coming down below 10, so 15. $500. What else? $250. $350. The total height, how much is it? 1050. So it is what, 60, right? 10, 50, 60, 75 total height. 75, 6550. And the last layer you have 75, you 75, 70. Okay. So now we have number of steel, we have the size of the steel, we have the distance from the topmost, so we can identify the geometry of this cross section from concrete and from steel. Okay, well, why don't we just run the code for the FID fopen. I delete the part that is unused. I'll get something up to function. We need what? File name only, enough. Okay. F skip. How many lines do I need to skip? 1, 2, 3, 4, 5, 6. Okay, 6 skips. Alright. And then F get line, get 45. The 45 is C lay. Okay, concrete layer. Number of concrete layer. And then once I get the concrete layer, I get the information here. So 1, 2 skip. All right, I need 2 skips. Okay, that is good. XY coordinates, well, not bad. XY core, okay, not bad. You can use this. What do we have? 500, 500. Okay. Need 3, right? And then CLAY, we string to num, and XY coordinate is equals to dummy. Okay, N4, fine. So we get all, and then we plot. Hold on. For I equals to 1 to clay, and plot plot layer by layer. We need to get the x and the y. Temp x or tmxy, okay, is equals to zeros. We need the plot, we need 5. You have 4 nodes, you need to specify 5 coordinates, 5,2, in order to make 4 lines. Okay, and then we calculate temp xy. So here is it. If you have the the slice, oops, one slice like this, let me highlight it up. Okay, you will have the line. We gonna construct this along this line. Okay, so this will be on the negative side, this will be on the positive side. Our cross section will be symmetry about this vertical axis. Okay, so I'm gonna start with the coordinate of this corner, and then lower corner, another corner, this corner, and then close down to here. Alright, so the first corner is the we're gonna get the tmxy 1, 1 being what, xy co actually it shouldn't be named xy co. Xy co, what is the data structure? 10 is the thickness, 500. Okay, xy co number I, 2, which is at the top, right? And this one is minus 0.5 multiplied by this number. tmxy 1, 2, which is the y coordinate. Y coordinate cumulative t, okay, equals to 0. This is equals to CUMT, cumulative thickness. Okay, which is now 0. tmxy, what else? The second node, right? So 2, 1. The second node was supposed to be minus 0.5 multiplied by xy co I, 3. 3 is the width of the bottom layer of the concrete, and tmxy 2 is equals to CUMT minus, okay, minus xy co I, 1, which is the thickness. Okay, tmxy, I should copy. 3, 1, 3, 2, 4, 1, 4, 2, 5, 1, and 5, 2. Okay, 3, 1, 3, 1. What is this? 3, 1 is the minus tmxy21 tmxy22 same y coordinate 41 is the corner here 1 2 node number 3 node number 4 is this upper corner which is same y as this one 41 is actually like 1 but opposite tmxy 12 and this tmxy 11 tmxy 12 okay I get all 5 nodes then that's gonna make the plot so tmxy 1 comma tmxy comma 2 use the blue line it's a hold on axis equal and function save it so change the name read section can I rename here okay what's gonna be the file name x cross-section 01.txt yeah end node where is it line 17 okay xy core is clay save it and call it what is going on why is it going out well first of all why does it print out let's check tmxy what I did there I think I put here okay now it okay but the point is that I get this figure it is added to the right I get the 0 here and come down here let me see what it reads over here $45 okay $45 so it picks up and then dummy XY core let me see how XY core look like I Actually, this is easy one. Shouldn't have bug in there. XY code turns out to be, well, it looks good. Okay, got it. So, easy thing. CUMT is equal CUMT plus TMXY. What's it? Okay, minus because it's coming downward. TMXY. Which one? 1? Oh, no, XY core. It should be XY core. XY core I1. Nah. Done. Yeah. So this is our cross section. Looks ugly. Eh? Need wider flange. That's fine. Okay, let's play with this ugly cross section just for the sake of learning. Over here 75 centimeters. All right. So now it visualize you this. Next, what else you want to visualize? The rebar. So come back here. I delete this rebar. Where is the rebar? Okay, so I read concrete layer geometry. Read the number of concrete layer. Okay. F skip line. Now we're gonna read, but read longitudinal reinforcement description. Home. Okay, longitudinal reinforcement. So we have skip line 2 lines. Okay, and we get this number, and this number will be converted to num to string. What is it? This is number of steel layer array. Okay, number of reinforcement layer. We get number of layer. So we get into the for, right? I equals to 1 to array, and then in that for we got to skip a bit. 1 2. Okay, we have skip 2 more. So f get line string to num again inside 4 rebars, diameter and distance from the top. Okay. Do I need to store? Yeah, I need to. So reinforcement equals to zeros, array and comma 3. So reif of I comma this is equals to temp is that done this way? Yeah. Oh, which is dummy then. Okay, dummy. We use the dummy. Okay, dmmy 1 comma this. So I get the reinforcement information in there, and then it's time to plot the longitudinal. Okay, plot longitudinal reinforcement. Use the same graph for I equals to 1 to array for j equals to 1 to number of reif I comma 1, because you have this many circles to plot, right? And then so I put the coordinate. What will be the name? Let's make it the temp being zeros. I need 8 points. I have 9 2. Okay, so one circle, I will represent the circle by the octagon. 8 points, 1 2 3 4, and then 5 6 7 8 in between. Okay, so 8 points octagon will represent the circle. Just the easy way. You can make it more circular shape, but waste of my time. So make it octagon shape. If it is so, then what? I need 9 coordinates. First, I need to get the center of each steel. Okay. So center of each. So steel will be somewhere here. If you have 1, you have 2, you have 3, you have 4. Okay, so first of all, the coordinate from the top is easy. The coordinate along this direction, we need to know the covering on the side, right? So I add one thing then, side covering. This is a layer, right? Then this is to be 4. Okay, and that has to be 3 because I got to skip line. Okay, I change this, I have more lines. Okay, so side covering, how much for the top layer? Need 50 millimeters covering on both sides, or 40. So that includes both the concrete covering and the stirrup, the hoop reinforcement. Yeah, I mean the clear is from the stirrup to the surface, but the side covering, I mean over here is the clear plus the thickness, the diameter of the stirrup. Okay, and then add up with the half of the diameter. Okay, and I define it side covering, which is clear cove plus diameter stirrup plus 0.5 D. Okay, it should be able to understand that. Let's make it 50. Okay, the other could be like 30 for small steel. And make it 50. Alright. So come back here. Fourth parameters. Okay. Temp. Over here we need to figure out the x and y coordinate for processing in the brain. Center x and center y. You first need the center of each circle. Alright, and then you can construct the circle accordingly. So center x, center y first. Center y is easy because it is equal to the number here, distance from the top, the third one, which is IEIF, I comma the third one. Center x is going to be minus 0.5 of the thick that layer thickness. We got to look up for the we got to look it up in the concrete, right? Kind of lazy to do the look up. Okay, I put a concrete width. not quite automatic. What, 300? 500? Okay. 100? The last one, 300. So 4 to 5. Okay, yeah. If we look up, it could be done, but I don't want to spend too much time. You can modify it. What is REIF of I comma 5, right? Now we have 5 minus reinforce minus 5, and then plus the covering, right? The number 4, right? REIF I4. So this one is your first coordinate of the left one, this one. Okay, so we will add this distance. We will place the rebar on an equally spaced basis. Poop. Okay, now we get this. Then what is that distance? The equidistance come from the x. This is equals to REIF I comma 5, and then I need to minus 2 times of REIF I comma 4, right? And then I divide this number by number of rebar, which is REIF I comma 1, right? Okay, so x is equals to sin x plus x this multiplied by j minus 1. So it will be from that point, j minus 1 is 0, and then boop, boop, boop. Okay. So center of y is a sin y. It doesn't change. Actually, you don't need to copy this. I just put it here like this first. Okay, I have the temp allocated. So TMP comma 1 equal comma 2 equal, and then I copy this for really many times. 3 4 5 6 7 8 9. Okay, 9 points. Okay, 1 2 2 3 3 4 4 5 5 6 6 7 7 8 8 9 9. Yeah. Temp 1 1. Which point is the lucky point? So if we get a zoom in of this one, make 1 1 here. Okay, the first point here, second, third, fourth, fifth. Alright, just that. So it is x, which is the center, plus the diameter, which is this one, second, REIF I comma 2. I mean dia is REIF I comma 2. Actually, you don't need this dia every time. I put it down here, and then okay.
So can you put points as circular symbol?
Huh? Circular symbol, but the sizing, just the kind of my crazy perfectionist thing is there telling me that I cannot do it. X plus 0.5 diameter. Okay, that's it. Next, the y coordinate is just the y or the sen y, because y is not changing. Okay, done for the first one. The second one, x plus 0.5 dia should be, I think make it radius, 0.5. We're gonna make use of this. Okay, easier, radius. Okay, radius. So x, 0.7, right? 1 over square root to 0.7 or 7. Sure. Is that right? 0.7 or 7. Yeah. RADS. Whereas the y is equal to sen y plus, right? Plus. Again, this thing, not 0.5. 45 degrees, yeah. It will be identical, right? Then the third one, only the y. So sen y plus rats. For x, it's just the x, right? The next one, x minus rats. For the y, sen y plus fifth node, x minus rats, y is sen y. Sixth node is this one here. So it is minus rats, y is sen y minus seventh x is x, y is sen y minus rats, and then x plus rats, and then sen y minus, where is it? Sen y minus, yeah. And then repeat this one here. Yep, Okay, then plot temp what temp 3 send this switch, right? Thank you. Great. Eagle eyes. Okay. Temp, comma 2. Make it red. N4. Okay. Try it. We'll see. Wow. Okay, yeah. But a few things. I think it is sort of shifting. It's not centering. Something and the minus sign. Yes. Fine. We can figure out. So send y is going to be minus that one, the first thing. But the program is so slow. Maybe the math octave itself. Yeah, it's not done right. It is something. The space here is coming from this subtract with this already. Okay, check. So the x was sort of a little error. Where is it? Okay, center of x is equals to minus of 0.5. The width of that, and then the 4 is fourth one is a covering. Okay, clear covering. So this is a start x, which makes sense already. And there's 1, 5 minus 2 times of the total covering to the center. Okay. Divide by minus 1. Okay, one thing, clear all. Oh, okay. What? Oh, okay. Clear all. It clear the variables. Okay, dokie. All right. Nice. Actually, this is not good for the software manufacturer, software production house. Safe does not like that. So, then you can later draw the other stirrup reinforcement, etc. Basically, for the data structure we have, I think we can still modify by prescribing the confined core and the unconfined core. So yeah, we can put some, maybe a few input over there. You can add in a few columns of the unconfined core. So now we have up to here. We can construct the moment curvature. The first part where the cross section is still solid and concrete still carry the tension, we can come back to fix that, which is very easy. We can do it like after crack. Okay, we can produce the after crack. Okay, let's finish up the business of this unconfined core. Unconfined core, okay. Sort of administrative issues, but you cannot run away from it. Let's take a quick break from my brain. Let me continue here. I'm gonna do something with the data structure just a little bit to make it possible to incorporate the confined core. Okay, I think just do it in one shot. So of here we can specify the confined core area and unconfined area, right? For the confined top and the bottom, width of the confined and width of the unconfined at the top and the bottom. Okay, so unconfined core, for example, for this case is 500, and at the bottom 500. Insert. This is the width of unconfined. Okay, so if we know the width of the unconfined core, unconfined layer, then you can compute the confined one. Top, bottom. But I'm not going to plot it. It is total width. Okay. So this case, I think we might have the top two layers being unconfined concrete, because it is the covering, you don't have the stirrup. And then unconfined concrete, once you are below 2 centimeters, it is encased inside the confinement. So you have what, maybe 3 centimeters on both sides, 6 centimeters. 60. Okay, you'll be having this until somewhere around here. So I'm gonna copy up this 60. Right, so this zone, we have two kinds of concrete. We have confined and unconfined. Oh, well, this one is still, no, this is 60. Okay, same. No. Yeah. The original one was correct. All right. 500 and 500. It's not actually 500. You got to subtract this zone. This zone is roughly about 6 centimeters. So it is like 440, right? Unconfined part is on the side because it's not the whole section. It is like almost the whole. But this part, it is confined from the web also. So 450 is unconfined. And then over here, unconfined core is 60 or 40? 40. For the web, all the webs, 40. And then you come down to this point here. The width of this thing is, oops, oh, what is, 30 is the thickness of the, okay. Well, I don't care, right? Because now it is under tension. So whatsoever number you put in, you will, it doesn't really matter, basically. So I'll just put some funny number. But okay, let's just make this, well, the point below this, okay, being like 0, 5. Doesn't matter. Okay. So the data structure turns out to be more complicated as we incorporate. Oops, what? Oh, yeah. Okay, just 0. I think, okay. What? Width of unconfined concrete. Top. Okay, width. Of unconfined. Okay, save it and correct this. So where 2 3, right? This one, right? 3. Okay, and then XY core, turns out to be 5. The plot will not be disturbed, but we just have the unconfined concrete. Okay, so our model will be able to incorporate both of them. We can use both models in this program. Right. So basically, what are the information that we will get out take out from this. XY core is not that necessary. Okay, that's a lot of things. I think my eye cannot catch the thing is which is going on here. So okay, XY core is one thing. So this one is XY core, right? This is steel. CLAY. Yeah, we need that. We need XY core. We need the R layer. We need a layer. We need IF reinforcement. We just plot it. Okay, yeah, that's just a cosmetic issue. We open the main then. Main just with section. Sect analysis. We don't need anything. Close all. Yeah. So top here, I don't need this. And then mainframe. Okay. The other thing, we don't need this. Okay, we're gonna obtain information from input file, which is this one here. We will have more, but not right now. So first we need to construct actually the same thing, but we will have one curvature first. Okay, we apply one curvature. We need axial equals to some number, so depends on what you prescribe. Basically it should be here, AXIL, which is the axial force, so for the beam this is 0. For the column, the sign should be clear, so people specify this correctly. Let me put in here AXIL, which is the axial force, positive for compression, negative for tension. Okay, just for this case in our calculation. Okay, axial force is there. So the algorithm is nothing more than just keep finding the strain. Okay, we have the curvature. If we specify the strain at the top, okay, to be just one number, then we be able to compute the corresponding strain in other layers. So curvature has to be specified because we're gonna have the moment versus curvature plot. So we're gonna put many different curvatures. We keep adding in the curvatures. Okay. So what is the limit? That will be our job to figure out. But now we need to make the routine that works for one curvature. Okay. So the routine that works for one curvature, function section equilibrium EQM, section equilibrium. So this function, well, we're gonna call this many times. When we call this function, we need to get what? Curvature value, right? Aside from curvature value, we will need the properties of the cross section. We get curvature, we get property of the cross section, and then the trial and error or the computation for the strain at the top or at the bottom, whichever, okay, will be made. The thing is that the final goal we have is the moment. Moment. Okay. So moment will be just one number. Moment corresponding to the given curvature at equilibrium. Okay, 60, great. Curvature, CURV, curve is a curvature which is generally specified. Okay, so the only one thing it gives out the moment, then you specify the curvature from the outside and then it gives the moment back. You'll be able to plot moment versus curvature. Okay, so inside here, that's gonna be the it's going to be the equilibrium of the cross section that we vary the strain of the concrete. So first of all, the big loop will be the trial and error loop. Previously, you remember we used the goal seeker. So the goal seeker, we have the goal seeker algorithm. Basically, it is the trial and error. So it could be the bisection, it could use some other algorithm. Okay. So let me think. Goal seeker. No. We need. Let me draw for you. The curvature is here, and okay, this could be the cross section. So for one given curvature like this, your cross section could be like this. This is your cross section. Okay, this is the neutral axis. So one given curvature correspond to many neutral axes. Here or here. Okay, so you have two variables. Yes, you specify the curvature, but you need to find the equilibrium state that actually ties up with location of neutral axis. Or in this case, the easy way, I think I use this line. So I say that, okay, the strain at the top I can vary, okay, and as I do that, I'll be able to adjust the neutral axis at the same time. You can either say that the location of neutral axis is from here to here, or you can say that strain at the top is this much or this much. All right, it could be done either way. All right, so the thing is that we're gonna do the try and error. The try and error we do, we can just do it by the bisection method. Means you come up with 2 points, maximum possible and minimum possible. For example, 0 strain in concrete and 7,000 microstrain compressive strain in concrete, because the 0.002 times K, which is 2000 K microstrain, is the max, is a F prime C, corresponds to F prime C. So if the concrete is ductile due to the confining effect, you'll be able to go further and further. I think 7,000 microstrain is quite a lot already for concrete, so it is like not likely. Then you have 2 possibilities. First, which is a 0, and the second is a 7,000. From 0 you get bisection means you need 3. So you have another one. Okay, this equilibrium, this state, and this state. Equilibrium could be somewhere in between here to here. All right. The point is that between this point to this point, okay, you can check the error you have. This one you get one number. What is that number? That number associated with the P. So axial force, if you put one configuration, you get one axial force. This one will produce one axial force, and this one will produce one axial force. For example, if this axial force correspond to this, is like minus 100, corresponding to the curvature which is in between 3,500 microstrain at the top, you might end up with 10, and this one gives you a lot of compressive force, 500. Okay, this is so called the bisection method. So you evaluate in these 3 given possibilities. Now you can see that here to here, you're not going to get 0. 0 locates somewhere between 3,500 microstrain and 7,000 microstrain, right? So from here, then you make another bisection. Another bisection will come from this. So you take 35 plus 7,000 divide by 2. 3,500 plus 7,000 divide by 2. You get the point in between. You evaluate the strain at that point. At that point, you might get right now you have 10. Maybe you get minus 40. Oops. $10. Okay. 10 minus 40 and 100. So we apply the bisection again. We know that you should do the bisection in here. So you get the value evaluated there, and then you pick the right side. So computer is fast, just let it run. You can do bisection for like 50 times, 60 times. What will be the resolution? Maybe that is going to be the question. What is the resolution? So the first resolution is, if you apply bisection for the first time, you get 7,000 divided by 2. 2 times, then you get half of 3,500, right? If this is under the assumption that concrete just fail at 7,000. So if you do it for this many times, like 100 times, then the error will be 70 microstrain. If you are not happy, then you can go like 7,000 times of bisection. It's not gonna make 7,000 microstrain. Oh, actually, the bisection there are algorithms that is good for. I feel like it is progressive. Why is it half down and then half? Okay, and then half. Hey, not like that. It is half down. It is half down. So it is 2 to the n. Right? Divide by 2 to the power of bisection. So make it. Okay. So if we make it 10 times, you get 6 microstrain. Yeah, that will be too stupid bisection. That is every microstrain, 1 to 7,000. You don't need to do bisection algorithm, right? Then I try an error, 0 microstrain, 1 microstrain, 2 microstrain, all the way to 7,000. That is a stupid algorithm. So if I make it 20 iterations, then this is less than a microstrain. Let's say, 1 microstrain is bearable for us. How many times? 15 is it is quite a good job. 12. Yeah. Okay. 15. Okay. It's just if we just make it 15, then it is good. Error will be quite small, so we can record the error if you want. Okay. Roughly 15 times. What if I just make it all the way to 10,000 microstrain? Yeah, still good. Still less than half microstrain. Okay, so we're gonna do the bisection. Okay, that's I think as much as we can go today. I'm gonna go for like the big picture of the bisection, the algorithm of the bisection. It has to be elaborate. Later, we are going to go push through lunch to the to the evening if we get everything. Just try to get everything done. So it has to be while loop. Oh no, it's nothing to do with y. I can just do it like for I equals to 1 to NBST number of bisection. Okay. So basically NBST, I'm gonna make it like 15 for now, associated with the resolution of strain being associated with the resolution of strain equal to 10,000 micro divide by 2 to the power of NBST. Yeah. Better have this for the record, because in the future I may not come back to this point and then wonder why I use 15. Okay, NBST, we get the satisfactory one. So what are we going to do? We will evaluate the entire cross section. Okay. At lower point. Okay. And then middle and higher bound, higher how to say, higher maximum possible, higher limit. Okay, so from 3 you get P, you get P and another P. Out of these 3 P, you figure out the range, which range to conduct bisection. So the range where, what is the condition? P lower, P middle limit, and P higher limit. So if the sine of PL multiplied by PM, we need to get the section if the sine of this is negative, right? So we have the sine of P medium times the P high. So just check the sine. Which one is negative? If it is negative, that means you are crossing the 0. So you pick up that range. Okay. And then once you get the range, you reset. So the PL, PM, and PH will be adjusted. If you are in here, then PL will be the same, unchanged. PH will be equal to the previous PM,
and PM will be just half of PL and etc. Okay. You define the new range, then you loop over to the top again. So you evaluate, and then find, loop over this. These 5-6 lines are very short in this schematic diagram, but it is extremely long when we start coding, because to evaluate the entire cross section, that means we're gonna have the subroutine that calculate the force in concrete layers, another subroutine for the steel layer. So yeah, that takes time.